various turbine blade manufacturing companies don't have same composition, although they make same alloys. And that is applicable for any foundry. Your chemical compositions for the same alloy would be similar. The trends are valid, but the exact values, this actionable information is different. And that's why if you just make one change, would not really, if you just take one change from another foundry, would not apply to your situation. You need to look at everything that goes into the pot. Now we take this example. The purpose is you can look at this for hours and still you won't have significant evidence. You can do loads of statistical tests. I mean, that is like working with, say for example, accountants and lawyers, and they will say that, forget about your information, tell us what you want to achieve. And then there are always statistical tests, there are always patterns in the data which support you or which don't support you. Now, we are not in that game. What we are interested in is not implying our knowledge to start with, or not imposing statistical distributions to start with. Give us a pattern in the data which can convert into confirmation trial. And we will see that if you just observe this, everything looks fine. And therefore, you might feel that, well, it's not composition, I need to look at something else. I'm not hesitant in making too many changes at the same time. That is okay. I want to see all those interactions and process parameters, measurable parameters. I don't want to know just the theory, because then I don't know how to implement that theory. I want to only speak in the language of measurable parameters and process response. The first step of penalty matrix. What we do is the deviation from process response is penalized. So we need to know what is the desired process response and penalize the deviation from the desired response. But we don't want to penalize in a binary mode, yes or no. We want to penalize in a linear way. But at the same time, we want to take into consideration outliers. If you just employ lower the better function, it just picks up maximum, minimum, and scale everything linearly. Now that will introduce outlier effects. We don't want that either. So what we do is pick up those thresholds that will say that, okay, anything about this line is undesired, and I give this as 100 penalty. So all these values get the same penalty. All these values get 0 penalty, and then I'll say that in between this is a transition period or transition range where they get between 0 to 100. You don't want to have step change, and then develop this complex fuzzy theory. That doesn't work. We don't want to make it very complicated. We want to keep it simple. And so what we are saying that desired response gives 0 penalty. Identify this worst performing 10 to 15% of observations. We got a very now mechanistic way of giving these threshold values. That's not a problem. But in principle, you are identifying 10 to 15% of bad responses, and then you accept, say, 30 to 50% as good responses, wherever it is. And then you are superimposing now this penalty function. And in between, the response is scale. This is simple. You can plot this bubble diagram in Excel, for all different observations. That's not great. The great thing happens now, which is what is very different, is get these penalty values and then transform or transfer these values onto your measurable factors. Now that is novel. You have seen scatter diagrams, everything everywhere in literature. But what we are saying now, that for every observations, even in our data sheet, I can go back to this data sheet. In this data sheet, every observation had one response value. Now for this response value, you are assigning a penalty value. Now forget about higher sampling rate. We can convert that into equal sampling rate. Lower sampling rate, if you are measuring something once a week, we can convert that into equal sampling rate. That's a matter of detail. We can do that. What is important is that every observation has a penalty value. So this boron value has a penalty value. This cobalt value has a penalty value. And that is the key thing. And therefore, we can transform these penalty values onto factor data. So in case of shrinkage variability, we came up with these penalty values, and that penalty value is transformed onto, say, zirconium data. Now this is the zirconium scatter which was available in the last column. Now this is the scatter diagram, which is traditional. Once you plot SPC diagram, statistical process control diagram, this is what you will see. But the missing link was not just looking at the scatter diagram. That doesn't tell you anything. Just say that, okay, it is within the limits, and maybe I got one outlier, and done. But once you transform these penalty values onto each, because each of these data points has a penalty value. We've seen that in data set. Now you plot the diameter of this bubble is proportional to the penalty value. And you assign that penalty value to each of these scatter, and then you see a completely different pattern. Because what you're saying, if these values of zirconium are in the bottom 50%, then there are a number of values where the process response is undesired. Because you already define the deviation from the process response is defined by the penalty values as undesired and desired. And then you say that if the zirconium is on the top 50%, then there are a large number of values where you got your desired process response. Now this simple data visualization tool has changed the perception. Your scatter diagram are now become more meaningful because they are giving you trends. So what we are interested in are the regions in this scatter diagram range which we can implement on the shop floor. So we are interested in top 25%, we're interested in top 50%, bottom 50%, middle 50%, and bottom 25%. So we come up with these groups. So we convert continuous data into these discrete groups so that we can implement that into confirmation trial. We're not interested in the regression equation. We don't want to have this magic equation which has got 20 factors and one response and then say that each coefficient tells me the strength. It works on simple problems, on linear problems. It doesn't work if you got large number of factors. So the logistic regression or other regression methods, that is not the purpose. We're not interested in those coefficients. Life is not that simple. We're interested in these regions because that is actionable information. That is the instruction that they give it to operator and can be proven in the confirmation trial. But at the same time, evidence that you can use it into your quality control meetings. But of course, visualizing this defect is, it's hard. You see the trend, so you got to go further. And then you can transform that into this penalty matrix format. Now to make life simple, we need to then make various bins. And the way you make bins is come up with this minimum value of this zirconium scatter, and then you got maximum value, and then get a median, not mean, median, halfway through. If it is arranged in the ascending order, you take minimum, median, maximum, and then values in between. So you get different quartiles. So the first quartile is between 0.019, 0.019, 0.023, 0.026 is median, next quartile is 0.032, and this is 0.05. And the spread was between 0.019 to 0.05 for zirconium. Now what we are saying that quartile 1 is this range, quartile 2 is this range, quartile 3 is this range, quartile 4 is that range. So now you are discretized into 4 quartiles, and then you get variety of combinations. Quartile 1 is bottom 25, 1 and 2 is bottom 50, 2 and 3 middle 50, 3, 4 top 50, and quartile 4 is top 25. So you start seeing those patterns, and then make these bins. Of course, in the analysis, you need a continuous function. Otherwise, a small change will cause a big difference in your solution. But forget about those mathematical equations. If you want to visualize that data, you make these bins 0 to 20 of penalty value, 20, 40, 40, 60, 60, 80, 80, 100. So you make 5 bins because the penalty values are deviations from your business response. And you're given this nice penalty values, top 10 to worst performing 10 to 15% get 100 penalty, 30 to 50% of good values get penalty values between 0 to 2, in between is a linear spread. Now that is then bin, you got 5 bins here, and then you got these quartiles here. If you have discrete parameters, then you can have operator name or operator skill set, or furnace A, furnace B. So you get discrete parameters as well. Continuous data is also discretized, and then you put everything into one pot, and then you start counting these bubbles. So here, there are 13, 9 plus 4 observations with high penalty values. So it's a lot of deviation from the desired process response. Whereas here, you get 16 observations which were good. And then you will say that, well, it's not really good as compared to here. You will see, you can watch individual quartiles as well, but then you can see that there are only 5 components which are bad if you add high zirconium. And then there is one with intermediate penalty, and then you got 17 plus 5, that is 22 observations with 0 penalty or 0 to 20 penalty. Now, if you give this information, the analysis is quite simple. And then you apply to your domain knowledge that, yes, I think there are 5 papers. I read that paper and somebody did this experiment, and if you increase zirconium, it's good. It reduces shrinkage. But I don't know why. So then you need to refer to the books. You need to refer to the literature to identify why there is that trend. And then you start adding that, and then those trends become useful. But then trends on their own are not useful, because this is your product-specific process knowledge. Instruction to operator, keep it in this range. But then map that with the trend which is available in the literature. And that needs to be done at the point of need. So when I'm looking at this, our tendency is to go into Google, find out all the papers. But that information doesn't exist. Okay, it could be controlled. Go into the portal, go all through the papers, and then you get, okay, I got these 5 papers which demonstrate this trend. And that is what needs to happen before you go to your quality control meetings. We can now go one step further, because we're already into defiance mode. So we don't have to agree the interactions as defined by Six Sigma. We got to look at interactions as what we perceived in the shop floor. Now, if you're into this bubble diagram phase, then replace this axis and get zirconium here and boron on this side. And all these penalty values will be transformed, because remember, each point on the scatter diagram has a penalty value. And therefore, you will get this, each point, the scatter diagram just becomes bubble diagram. And then we are interested into a region or a cluster of points or an area in this zone, which could be this region or this region or this region, any combination where there is a concentration of points with high penalty values or concentration of points with low penalty values. And that is interaction. Because what it really says that if zirconium is in top 50%, that is zirconium, top 50% is this region, and boron is in bottom 50% region, this is boron, and this is bottom 50% region. So when they occur together, is only this is the common area where they can come together. So if you control zirconium in top 50, and if you control boron in bottom 50, that is, this is the common area, and then you see this is a statistic. There are 15 observations with 0 penalty, and out of these 5 components, now there is only 1. So the 4 defective component moved away. And then we say that in comparison to these 3 combinations, this particular one is much better. And if you see this data into this format, again use domain knowledge that why zirconium and boron come together and what happens. And once that is available, cross-checked with the published literature, you can then say that, well, it makes sense to keep zirconium in top 50, boron in bottom 50. You create a hypothesis, and then that is discussed in your quality control meetings. And this will then become a hypothesis, confirmation trial, test it, and then it will eventually help you to reduce your rejection rate. But this is just one. You need to look at number of things. But this is the way you start visualizing your data through penalty matrices. We're not interested in statistical interactions, which you see in statistical packages. We're not interested in that this is good because this is the p-value. We will just want to visualize data, because it's your own data. Visualize that data, cross-check with published literature, and then do confirmation trials. So even if it is, once you see this with a very few observations, you got a trend, which way to move. And that is how you start tweaking your process. Information, again, is the product-specific process knowledge with actionable information. And we are really interested in this tolerance limit, We are interested in those clusters which interact in order to meet this desired goal, because the deviation from the desired goal is penalized. What we are saying that industry is spending a lot of money and resources in collecting data. Now we have to just take few small steps so that it is reusable. And the moment it becomes reusable, we apply this deviation from the process responses. Now these process responses can be conflicting. Shrinkage, optimized chemistry for reducing shrinkage is different to optimized chemistry for increasing tensile strength. They contradict with each other. So how do you find the common platform which will say that, okay, I'm going to minimize shrinkage, but not at the cost of tensile strength? And that requires a quiet hour of analysis of these reports and this variation. But it's possible, and we'll see that in the presentation in the afternoon. But once you do that, you can look at interactions in this way and then come up with these regions so that effectively now you are quantifying these links. You can't use regression analysis or neural networks to quantify this trend, because we can always come up with mathematical algorithm which will give this variation of this trend. You know, I spend a lot of time to be able to quantify this robustly. And then what I've really found is that this simple technique is the only way to gain insight into these interactions and main effects. Then you convert that into an Excel report which we can use to further process that data and then come up with a confirmation trial. And I think these are the simple steps which gives you that step. But then that process knowledge then we develop the library of this process knowledge, and then check with the published literature, so on and so forth. So what are the advantages of this approach? It identifies main effects and interactions in a different way, but which is more meaningful because it's your own data. It's not telling you something new. It's not putting some distributions on your data. But then that is the key thing, is the measurable factor ranges. So you can implement that into shop floor in order to meet desired business goal. That is the buzzword, because any deviation from a desired business goal is penalized. And then you create new hypothesis, and that helps you to turn insight into actionable information. So if you're getting data from, say, 4 suppliers, sometimes the quality goes down, sometimes quality go up, and then you'll see this penalty matrix, define the variation from the penalty, combine those 4 foundries' data together, and then you get this common confirmation trial goals. And that knowledge can benefit all the foundries which take part in that project. And that will turn insight into actionable information, to confirmation trial, and once it is done, it becomes process knowledge. And that is simple to use, and that's the way to retain that knowledge. And once you get library of such reports, it's a lot easier to go back and then see what had happened, what were the ranges. And that evidence is useful in your quality control meeting. So the decision is not really lost. It's just that you got now more information and more evidence in the quality control meeting rather than just rejection data.